Hi everyone, my name is Steve. Today we're going to go through breadth-first search. This is one of the simplest algorithms for traversing a graph and also the archetype for many important or advanced graph algorithms. For example, Prim's minimum spanning tree or Dijkstra's single source shortest path algorithm, etc. Given a graph, we'll call it G, with number of V vertices and the number of E edges, and a distinguished source, we'll call it B. This breadth-first search will systematically explore the edges of G to discover every vertex that is reachable from this B starting vertex, and it computes the distance with the smallest number of edges from B to each reachable vertex. It also produces a breadth-first tree with root B that contains all reachable vertices. So for any vertex V reachable from B, the simple path in the breadth-first search from B to V corresponds to a shortest path from B to V. And another thing to note is that this algorithm works for both directed and undirected graph. And the reason why breadth-first search is named so is because it expands the frontier between discovered and undiscovered vertices uniformly across the breadth of the frontier. What that means is the algorithm discovers all vertices at distance k from B before discovering any other vertices at distance k plus 1. Okay, to illustrate this, we'll define a few things first. We'll use EQ, which is very standard as we learn about breadth-first search, which we always apply a first-in, first-out queue. As you see here, we'll use a queue. And a few other things we want to define, we'll use different colors. White, which means is the vertex has not been in-queued yet. And gray, which means this vertex is currently being visited. That means it's in the first-in, first-out queue. And black, that means this vertex has been in-queued and de-queued already, which means it has finished. We have finished visiting this vertex and finished traversing all of its directly adjacent neighbors. And another thing to note is that for the graph, we're going to use an adjacent list to represent a graph. So initially, all of the vertices will be in white, except the starting one, which we will call it B. So the B will be our starting point, and we have B initially painted as gray because that's the one we're going to start. You can pick anyone to start. You can pick A, C, D, G, H, any one of them to start. That's fine. For the purpose of demo, I'm just going to pick B. You can reason it as B stands for beginning. That's fine. We'll just use B to start. So we paint B as gray in the beginning. So we have B in the queue. And here we'll construct a breadth-first search tree here. And in the beginning, we have infinite in the vertex, which means they have never been discovered yet. So this will be a number that is the shortest path to this B. We'll call this one B to be the root. And also, one more thing to note is that we'll have a predecessor, or we call it a parent concept. In the beginning, B is the starting node. So B's parent or B's predecessor is null. But for every other node, as long as they are connected, as we can see in this example graph, they are all connected. All of them will have parents. Right now, this one is 0. Everything else has infinite because we don't know the shortest distance yet. With all of these defined, let's walk through this breadth-first search. In the beginning, we only have B in the queue. Next, what we will discover is all of those vertices that are directly adjacent to B, which is what? F and A and F, right? Both of them are directly adjacent to B. So what we will do is we will in-queue both of these two vertices into this queue. At the same time, we'll de-queue B. This is what happened. B is marked as black, which means it has been in-queued and de-queued. And then we in-queue the two directly adjacent neighbors of B. So A is in-queued and F is in-queued. In which order, that is totally fine. You can put AF first or FA first, but however you put it. So if you put FA first, the next time you're going to de-queue F first, because remember, this is a first in, first out queue. This one is black. The reason it's black is because it has been in-queued and de-queued. Right now in the queue, we have F and A, and both A and F's parents or predecessors are B. Now we have finished traversing the first level. That's why it's called breadth-first search. We go as wide as possible on the same level, right? So the first level is finished, and then we traverse the second level. We de-queue things in the queue. So next one to be de-queued is F, and F's direct adjacent nodes are C and G. Again, it doesn't matter G and C or C or G. So we put C and G into the queue and we have de-queued F. So after we de-queue F, F is marked as black. Then we put C and G into this queue. Okay, now what's next to be de-queued? First in, first out queue. Next one to be de-queued is A. And A has another adjacent child, which is E. We'll mark the node A as black and then we'll mark its child E as gray. great. E is here. So at this point, A and F, or F and A, these two adjacent nodes that are adjacent to B, now both have been visited. That means we have finished traversing this level, the second level. Again, this is why it's called breadth first search. We visit every single level first. This level has been finished. How can we control this order? Because we used a first in, first out queue. Next, we'll visit the next level. So next one to be dequeued is C. So C is going to be marked black, and C's adjacent unvisited child is D. It will be like this. D is added here, and C is marked black, which means it has been dequeued out of the queue. Next, we'll visit G. G is pulled out, and G has only the other unvisited child, which is H. So H is pulled out. And again, all of these numbers, see, 1 just means the distance to the root node is 1. 2 means the distance to the root node is 2, right? I hope that makes sense. So back to here, we have dequeued G. So we added the unvisited adjacent node that has a parent called G, which is H. We added H, and H's distance to root is 3. And then we'll continue. We'll continue to dequeue E. E is dequeued, and E doesn't have any other unvisited children. At this point, the third level has been finished visiting. So at this point, we have finished visiting the third level. What do we still have in the queue, which is D and H? So we'll continue to dequeue both of these. We'll dequeue D here. D doesn't have any children. And we'll continue to dequeue H, which doesn't have any other children. At this moment, we have finished visiting the last level of this tree, and we have finished constructing this tree. And the queue is empty. In the actual code, when the queue is empty, we'll just finish. We'll just break out of the loop and finish traversing this entire graph. That's just how breadth first search works. You'll be given a graph, and you can use breadth first search and use any one of these vertices as the start node to construct a breadth first search. Along the way, you're going to visit every single node as long as it's connected to the root node. All right, that's done. As I said, one thing to note is breadth first search will always produce a tree, and the root of the tree is your starting node. Now let's take a look at the pseudocode. So for each vertex U, we'll call it U in the graph, we define 3 parameters, extra parameters to help us understand. First one is color. Initially, everything is white, meaning they are unvisited and they are not in-queued in the first in, first out queue. And distance is all infinity, and predecessor is null. Next, we'll define B as the starting point. So we'll paint B to be gray and distance to be 0, meaning that's the starting point. And then we'll have B's predecessor. B is the only node that has a null predecessor because B is the root node. And then we'll initialize a empty queue. Then we put B into the queue. Next, we'll have a while loop. So we'll continue to visit. First, we dequeue the only element in the queue, which is the root node B. Now, for every vertex that is adjacent to B, for example, in the beginning, there's only one node in the queue, and we dequeue that to visit all of the adjacent nodes, which is A and F, if you recall that. We visit V. For each V that is adjacent to B, we visit them. If V's color is white, which means it's not visited. Only if it's not visited, we will do this. We'll mark the color to be gray, but for the distance, we're going to +1. That's how we calculate the shortest distance for every single other node. So 0 + 1 is 1, and this one is 1 + 1 is 2, and this one is 2 + 1, that's why it's 3. And then we also mark this V's predecessor as U, because A's parent is B, A's parent is B, and E's parent is A, E's parent is A. Makes sense, right? In the end, we in-queue this V into Q, so we'll in-queue A and F into this queue, so that we can continue to traverse A and F's children. Next, we'll mark U as visited. That means we have marked B in the beginning. All right, that's the entire pseudocode of this breadth first search. Again, this is the simplest and very useful and the founding block of many more advanced graph search algorithms. I hope this does make sense. Now let's talk about the time complexity of this breadth first search. Suppose the number of vertices is V and the number of edges is E. Because the in-queue and dequeue operation is only going to take O1, and again, we're using adjacency list as the representation of the edges. So as you can see in this pseudocode, we scan the adjacency list only when this vertex is dequeued. That means we will visit every single edge at most once. So with number of edges as E and number of vertices as V, so the time complexity of this breadth first search algorithm is going to be V plus E. V is the number of vertices and E is the number of edges. We only visit every single edge and every single vertex only once. All right, this is the entire algorithm and time complexity and how it works. I hope this video does make sense and does help you understand breadth first search. This is the founding block of many more advanced advanced graph search algorithms, and it's a very powerful and useful algorithm for graph traversal. If you like this video, please do me a favor and hit the like button. That's going to help a lot with the YouTube algorithm, and don't forget to subscribe to my channel as we continue to go through a lot of very interesting algorithms and data structure problems. That's it for today's video. I'll see you guys in the next one.